Alrighty, well thank you again for coming in today. It's really awesome to be here in person again with everyone. Finally, it's been a long time since we've done this, so it's nice to see faces and full bodies, not just headshots, which is really cool. What we're here to talk about today is because it's meant to be all about what's the next step within 3D printing. Where do we apply this, how do we apply it, and how do we enable applications as we move forward. And the best way to do that, of course, is combining efforts, right? Combining the market power, combining technologies, and really looking past the basics and looking down the road of what's in the future, what's our vision, and how do we actually align that vision. So today we're talking, of course, about how do we enable the applications with that complete AM architecture in mind. To kick it off, my name is Mike Schorr, and I lead the application developments and consulting for the Americas region of DyeMansion. Big background in the manufacturing processes, but everything I'm doing at DyeMansion is all involved on materials, properties, application-specific projects, and really exciting pushes like we're going to talk about here today. And I'll pass it on to Tim here in a second. I guess you actually have your microphone, right? I do. Perfect. And Tim can introduce himself.
So, good morning, afternoon, wait a minute. My name's Tim Heller, yes. I am at Stratasys responsible for the commercial activity in the Americas for our new powder bed fusion, the SAF product. To give you a little history, I did join Stratasys way back at the beginning, like 1993, so I've done a lot of, let's say, helping people navigate this new technology from FDM on through to PolyJet and et cetera. So it's really exciting today to be able to tell you about our new technology we announced last week. So not only will we be talking about our relationship with DyeMansion, but be able to bring you some details on what H350 is and what SAF is.
Awesome. Yep. Thank you, Tim. And again, it's really exciting to have Tim up here as a real veteran within the industry. Super exciting to get that relationship up here. So let's see what we're actually going to talk about today. It's not going to take the full hour. We actually want to open it up pretty good for questions towards the end, so please think about those throughout the day, or this time period as we're talking here. But we're going to, of course, introduce some basic information about who we are. So for each of us, we're going to kind of talk a little background, really quick, brief, to understand where we are as company-wise, and then what we offer from a portfolio of its technologies. So it kind of encompasses what that path is, so we would just want to educate you a little bit before we get into what that vision really looks like. Of course, there's some big news to talk about as well, and we'll get right into that, but then we're going to also talk about how we align that vision to then enable those applications, right? The whole reason we're really here today is talking about parts, talking about ideas and future products as we move forward. All right, so a quick intro from the DyeMansion side. We are a continuously growing team. We have just over 90 people so far, and we have two main locations. Our initial headquarters, which is where we started everything, is just outside of Munich, Germany. And we have a brand new facility in Austin, Texas that we opened up officially only a short time ago, this past year. We've already been running parts out of there. We've actually had that space for well over a year now, but we've actually officially operated, and we've already processed a couple thousand units out of there already. We were initially founded in 2015 with a few different options. Initially, we based everything off of a simple idea of adding color to polymer parts. We learned really quick that we were not great at it. So we actually worked through a lot of different ways to create better surface finishes to enable color to actually look better at the very end of the day. So the idea of that is that we tried to work through the entire process, and we learned a lot by making a lot of mistakes, just as most of you have probably already learned yourselves. Where do we actually fit in on this whole idea of a processing chain? Now, of course, there's three main steps that come with printing. There's always the initial step, which is the idea, the drawing, and the design. This is, of course, for anything from that napkin sketch, the original idea, to the CAD file, the STL, as we go down that line. Then it comes the build process, which, as we all know, is a very, very big envelope of different options, whether it's materials, technologies, how we design better, how we implement that print into a part, and how we influence it in different ways, whether it's thermal properties, high details, whatever it might be. Really important process in the chain. And where we fit in is the very back end of all of this. We are the last part of the chain, the post-processing side. Initially, it's always been the last step that people think about. Unfortunately, that's probably the worst way to really do it, because the post-processing, as I kind of talked about before when we learned about dyeing, it only really works if the rest of the chain makes sense. So the design side is a big factor here. How do we design a part to get better? How do we then print that part to make sure it's going to work the right way within the post-process chain? These are all things that we've learned really well as a company, and we're trying to continue to educate the industry as we go to make sure that the whole point of this is that we all can actually produce the right types of parts, the right ways, and have the right mindset going into it to enable that very end result. So the way we kind of think about this is additive manufacturing. The goal of it is to create this as an everyday unit. How do we start thinking beyond the prototype, getting these parts now into the environment to become everyday parts? One basic way to do that, of course, is kind of camouflage. Get them into the market, get them into the areas where they're not totally noticeable right off the bat. In order to do that properly, we have to have the right type of finish where they start to replicate things that exist currently. If we're replacing a part, it's got to look a lot like that part we're replacing. If it's something that's totally new and has a crazy lattice structure, we might have to design that lattice structure with a proper finish on it so that it actually applies properly into that application as we go. So as Dimension, we really continue to think about that same vision always. How do we enable the future of 3D printing to become everyday reality, everyday life? And that's why we pride ourselves on the post-processing chain to create that enablement. We do that mostly through the two different facilities we have to help educate, and again, to create the opportunity to produce parts and also just give a basic user experience, right? So we have our main headquarters outside of Munich, Germany, and then we have our new facility in Austin, both of which we have all of our technologies there. Our main R&D is still done overseas, but both locations are totally enabled to allow you all to come on down, given current status, of course, but come on down, bring your parts, actually process them hands-on. The point of that is so you learn, because it's one thing to just sell the machine and get them out to the business, but then we still have to educate how to use that machine the right way to be effective in your own industries. So the whole point is to actually bring you on site so you can work with the systems, fail on the systems, and learn how to get better with each of those systems as we go, with your own parts, of course. Then the next side of that is actually helping you get started. So it's that small volume production. So in both facilities, we do have an on-demand service, that's how we call it. It's essentially a small volume bureau on the post-process side only. We don't have printers, actually. So we are totally agnostic from the printing point of view. But we always like to pride ourselves in being able to create opportunity is really all it comes down to. If you have the capability but you don't have the capital at the moment, we can still process parts. If it doesn't make sense to go to a service bureau for only 50 parts, we would work with you to actually start that process to enable you to then get yourself ready. The other side of that is we also have to prove ourselves sometimes. So that small volume production is to help prove the capabilities and how they actually can influence your part. Initially, well, up until a few weeks ago, where we kind of fit in from the technology point of view, we based everything initially off the powder bed side of technology. So your standard SLSs, your MJF side of things, and most of the materials within both of those regions. Over the launch of the PowerFuse last Formnext when we had it in person, and then a few extra developments with the DM60s, we learned that we didn't just lie in that one area of powder bed technologies. We could also apply some of these technologies to other areas of printing, whether it was the ULTEM type materials or other FDM based materials that needed a better surface finish that were able to be vapor polished. And then through our DM60, the dyeing process, we also learned that certain types of resin-based printing were also now enabled. So again, taking that basic portfolio and now applying it to all different types of technology. So a really exciting thing of how we fit in. And now what's even more exciting is that we can kind of look what's next. We always want to see what's next in the environment. And that's why we have Tim up here. But initially, or what we're going to talk about mostly is where does this new material, where does this new process lie within our lives? And how can we continue to push it forward? So right now, of course, the brand new technology behind SAF and the PA11 material that's out right now is something that we can fit directly into our process chain. And what we actually were thinking about and why Tim is even up here in the first place is something that's super exciting for us to announce. We did do a press release yesterday, but officially in person we can actually announce that Stratasys and Dimension have agreed to work together and create a partnership and a true alliance to actually enable applications at the end of the day. So what that really means is we're combining the strength and the market power behind the history, of course, of Stratasys, both the technologies from both of our teams, to really push it forward and create a complete reference architecture for high-value end-use parts and volume according to that, or adjacent to that, all through AM. So in order for you to explain a little or understand a little bit better, I'm going to hand it off to Tim for a few minutes here to talk more about SAF technology to help you understand how that starts to lay into the future life.
Let me see if I can get technical. This right button means forward, right?
Works so far.
Okay. Awesome, look at that. All right, thanks everybody. So I'm going to spare you like the long history of Stratasys, and let's talk about what Stratasys is doing today. And, all right, is there a trick to this? Okay, press it about 4 times and it works. So it's about Stratasys. So Stratasys, and a lot of you are probably familiar with us, but when we got our start, we were locked into one technology, FDM. Now, FDM, as you probably recognize, is very good at low volume, high value parts. And for the longest time, that's what Stratasys has done, even when Stratasys increased its portfolio to have FDM and PolyJet. By nature, they're high value, low volume parts. That's awesome, right? But there are 7 different technologies you're all aware of defined by ASTM, and only recently, Stratasys actually has expanded. We're into 5 technologies now. And I have to tell you that before I recently rejoined Stratasys, I told you I joined a long time ago, but I have been out of Stratasys, in fact the industry for a while, and I can proudly say I was retired, and that is one thing I do extremely well. I can go into my second retirement someday and I kind of know how to do it, right? But I get a call one day and said, guess what? We're going to go through a similar journey that we did when we were back in the rapid prototyping days, and we're going to start helping people with a journey into new ways to manufacture. We did it with prototyping, and now Stratasys is expanding into stuff that's not exactly low volume anymore. This is a first for Stratasys. And we've acquired now a couple of technologies, so we have more than one technology that leads us to higher than low volume. So I could say really high volume, but that all depends on your perspective, right? Is it high, is it mass volume, or is it just some volume that's way more than low? Well, this is some volume way more than low. We're talking tens of thousands of parts or maybe 100,000 parts in this type of technology. That excited me. And that got me, whoops, these are in automatic mode now. So anyway, that got me excited, and I said, well, to be able to jump back in the industry with a company that is really familiar and has done a lot of great things and get into a technology that's brand new for us, and that's powder bed fusion. So now powder bed fusion, as you all know, could be polymers, could be metals. Well, we're in polymers. That's our focus at Stratasys. In powder bed fusion, you could have laser sinterings. You can have laser-based, or you can have jetting-based or printhead-based. We are printhead-based. So today I want to tell you a little bit about what we launched last week, hopefully answer a couple of questions that might be circling in your head, and I'm sure I'm not going to do it completely justice, so afterwards you can come on up and we'll try to answer even deeper if you need. But let's talk about our focus. Our focus is about creating a technology that gives you consistent, repeatable parts. That's what SAF is about. To practice that, I'm talking to a lot of people who know what they're doing, so it's kind of actually a little bit intimidating, right? Many of you know more than I do about how to layer and how to do powder processing, but I'll give it my shot. So our focus here is as we put down a layer of powder, and then we follow along with a wide area print or a full width print of our XY plane. We have a powder application, and then we follow right along the back with a full width print head, which prints a fluid which is loaded with an absorbent material which absorbs infrared energy in sufficient quantities that as soon as I follow behind that with a high intensity infrared heat lamp, I absorb enough energy, there we go again, I absorb enough energy to cause melting in that area that I printed the fluid, right? I don't think that's new for a lot of you. You've heard about a couple of technologies that do something similar. Our execution is a little bit different. So one of the focus points here is you see us identifying point 1 and point 2. So that would be like in the 0, 0 coordinate, and point 2 might be in the maximum coordinate. In our case, that'd be about 12.4 by 8.2 inches. So if you go out to that coordinate, what happens is I spread the powder, and then I do the printing of the liquids, and then I do the the application of the infrared, there's exactly the same amount of time elapsed between each of those three activities in each area of that XY plane. And what that does is it gives us uniformity from every spot in the build, so that when we load up that build with a high amount of parts, we can expect a similar performance or the same performance from a part that's in the 0 coordinate to the one that's in the 812 coordinate, right? Now, when we do that, when we apply the powder is applied in what we call a big wave. So we put a big pile of powder, because what's happening? The powder is cool, the bed is hot. So when we put that big wave of powder, we're trying to keep it cool as long as possible, and then we get the powder on there and then have it heat up more uniformly. And again, it's about thermal control and thermal uniformity. Now, if we do that, then we're going to have an excess amount of powder that's going to reach over at the end, right? So we go left to right, always left to right, always left to right. When the powder reaches the end, it's going to fall in overflow. While the overflow immediately is plumbed back into the system and mixed with the other powder that's already waiting in the chamber. And in fact, all of our powder mixing happens within the machine. It doesn't happen externally. So when we do dosing, right, we do by the way, we're using PA11 here, and we mix typically at 70-30 mix. Although we don't lock the user into that, the user might adjust that, but that's where we do our testing at 70-30. So all that mixing or the dosing happens outside. We introduce the powder into the machine does the mixing, and as this process works, the powder that's in the process mixes with the powder that's already in the machine. Then on the right, you see a depiction of a head. So now Stratasys has a joint venture with a company called ZAR. And the company is called ZAR 3D that Stratasys has worked with to define this product and develop it over the last couple of years. Now, the description you see on the right is an illustration of a ZAR printhead, and that is a piezoelectric printhead. What's interesting about it is it's a high fluid flow printhead. So as you see the fluid coming into the print, as it traverses the XY plane, it's dropping out the droplets where we need for the solidification to take place. But the byproduct is, by flowing that fluid through at such a rate, it also regulates the temperature of the head. And by having a regulated temperature of the head, it allows us to be closer to the surface and get more uniformity as we print, right? Now, one thing that's interesting to say is these printheads are also used in an industrial environment today, which is a dusty environment, and that is printing on ceramics. So it already has a track record, and the way it operates, we actually don't include it as a consumable. This is just a permanent part of the machine. So it's not a device that has a lifetime that you have to replace a unit every period. It's actually expected to last a lifetime. And if it's wear out, it's included in like warranty and stuff like that, which is a little different. And I'll come back to why that matters in a bit. Back to uniformity, if we look, one of the focuses of us is to give you the uniformity in the XY plane, but give it in the Z, and also give it from build to build, and give it from machine to machine, like in variation, right? The example you see here is two different builds of the same in comparing the temperature. So you can look here at the temperature uniformity over two different builds on how the temperature was recorded throughout the entire build. Now, it's interesting for looking at uniformity, but also the way we've designed the product is to be able to export much of the data that I'm talking about so that when you do production jobs, you can also have data to follow your production. You can look back at what were the temperatures, what was happening when this happened. So that's able to give you a control of the process. An example of nesting. So of the properties I'm talking about thermally, it gives us the opportunity to have different nesting rules than a lot of people in powder bed fusion. So oftentimes you pay attention to uniformity in some powder beds, so I'm not an expert in every, but I hear that often you look at the uniformity of how much layer density you have from layer to layer. We don't really have an issue with that, which allows us to do a couple of things. One is because of the thermal control, we have We have a benefit in larger, flatter surfaces because, as you know, thermoplastics tend to curl and all that kind of stuff. But if you can control your thermals the way I'm talking about, then you have less of an effect of that. When you have less of that effect, then we don't have the same types of rules where you have to do what I said about layer to layer consistency, whatever. So we can actually locate horizontal surfaces anywhere we want. So in this case, this example of the build, it's 150 pairs. Actually, it's a printhead device for moving the printheads around the factory. But I have some examples here. But we're able to organize them in such a way that you saw that they're a little bit more efficient. That gives us a little more control over the nesting density as well. So our typical nesting densities are 12%. But you saw there, we could go much higher. We could go over 20 or whatever. We use 12 and the mix I told you to generate all of our comparative data, like mechanical performance and things like that, which we'll be releasing soon, but it's not available quite yet.
Awesome. Thank you, Tim. So that's good background on the technology from the print side, right? So now we already understood where the post-processing side lays, but to give you a really quick recap of what each of those offerings look like, we'll dive into that right now. So there's a few ways to kind of look at this. The first way, and probably the best way to look at this, is understanding what that final finish really should be, or what the desire is that you want. So from that, you can really look at, what does that application have to be? Is it something that's touching skin? Do we need certifications? Does it see water? Is it airflow? Does it really not matter? Is it a prototype only? All these things really apply and help you understand which process flow makes sense. So from the technology on the back half where we live, we have three main steps. There's cleaning, there's surfacing, and then there's coloring. The first step is key. Cleaning is always the most important step because without the proper start, nothing else really makes sense. Nothing else matters, to be really honest. Without the proper cleaning approach, you never can create a uniform, homogeneous finish on the rest of the part. So we have a few different offerings. One is our PowerShot C. So this is, I'll get into the technology behind it in a second here, but essentially it's just a cleaning that utilizes a couple of key features: fixed nozzles, rotating basket, alternating cycles, and deionization. All of these basically enable a repeatable process, which is non-destructive to the actual part, which is really, really important because we're not changing geometry, we're not removing any material, we're just getting rid of powder, that's it. The next main process is the surfacing side. Now this can be done in a couple of different ways. Now this is kind of where we have to think about what that application is. So one is the mechanical surfacing option, which is right now the quickest in the market to get there. It's only about a 10-minute process for standard build size on all platforms that are out there. It's again it's a non-abrasive process. All it is an impacting, create a more homogeneous surface. And what that does visually is it changes the way light's reflecting on the part, which essentially gives you a more uniform visual appearance of that part. Also increases the scratch resistance of the part with a few other properties as well. Again, just a quick 10-minute process there. Now, if that application needs to be watertight, for example, that's where vapor technology comes into play. Now, there are a few different options out there, of course. We have the Power Fuse, which is our vapor technology. And what this does is introducing vapor into a processing chamber, as we'll talk about in a second here, which enables it to actually create a totally sealed surface on that part. And this is really important if you need, again, that watertight, airtight type finish or something that's washable, for example. Now, to kind of step back a second here, over the last few weeks, we also just launched a few new technologies that were around the same ideas that we've already had, both cleaning and surfacing. These are the performance-based series. Now, this is that first step to what that factory of the future looks like. How do we enable mass volumes? How do we actually supply enablement of that next step of product? So the performance series are all based around the same concepts of technology, but it uses a little bit different of a setup. So it creates a belt loading from the front, allowing it for, well, robots, right? The next step in the manufacturing line. What's always next is eliminating the actual human interaction with the part. Eliminate the potential human error from the side of it, and that increases the repeatability of a part. Going all the way back towards the end now, the aesthetic side, coloring. This is how we start going back to what we were talking about at the beginning. How do we camouflage that item to go into normal, everyday work? Or is it something that, let's just say, apparel company A comes to you and says, we need seasonal palette red. This is the color code. it's really hard to try and find that color code from an off-the-shelf product. And that's where we can kind of come into play and actually match that color directly to enable that process to now be used in a real-world environment. So that was a quick overview, understanding each machine individually, and we'll go through this a little bit quick. Starting with the cleaning side, so the PowerShot C. What this really does, as we talked about, it's very simple. It's just on the depowdering side. But the key thing is it's powder removal, not actual any material removal. So we're taking a part right out of the powder cake, simple shaking off the part, tossing it right into the PowerShot C. Roughly 8 to 10 minutes, depending on the type of part, how fragile it might be, or what the application is. That part is then totally cleaned off, ready to go into the next stage, wherever that next stage might be. Let's just talk in basic product portfolio line here. So the next stage in this case would be the PowerShot S, which is the mechanical surfacing option. It's a very similar technology. So it is, again, a media blasting with a couple of fixed nozzles and a rotating basket. The key here is that it's actually a proprietary polymer blend of media. So it's non-destructive again. It's non-material moving on the part. It's strictly just knocking down those peaks and valleys to give a really smooth, homogeneous surface on the top. Now again, this is just kind of looking at it from a technical point of view, but think about it from the application side. One of the greatest examples that we have, we'll talk about it soon, is eyewear. Something that's on your face all the time. Half the population really has them. We currently are involved with millions and millions of units of eyewear a year that only use the PowerShot S as one of their main finishes, strictly because it still has that industrial look, but it applies a scratch-resistant surface that's also capable of being on a human skin, which is perspiration, skin irritation, cytotoxicity, all these things that come into play that a standard porosity type part right off the printer will not work that way. Looking at a little bit more of a technical side of things, going into the next system, the Power Fuse. So this is a little bit longer of a process, and this is using a vapor technology. Similar idea and concept as other vapor technologies that exist, and one of which, of course, we'll talk about soon, but Stratasys is why they're up here as well. Came up with these ideas long, long ago. Vapor technology has been around in the industry, both in metal and plastics, for a very, very long time. Over 20 years at this point, easily. We just kind of took it and advanced it a little bit, just like others have already done. Parts are suspended within a process chamber, so now we got to think about how we design that part maybe a little bit better. So this goes all the way back to that initial stage. Maybe we need to design a special mounting loop or way that we can suspend that part within a processing chamber to avoid any visual discrepancies or to speed up processing overall. Vapor is introduced into that processing chamber, and essentially what's happening is that vapor is now condensing on a part, allowing it to actually realign and reshift some of those molecules on the outer skin. Very, very minimal interaction there, and all it's doing is just creating a totally sealed surface. So now that surface can go right into an application that might need to be washed, whether it's in a medical environment, food and beverage type environment, or maybe it's just something that needs to have a glossy surface just for a visual aesthetic. And the last step of that whole processing chain is the color. Again, what we talked about a little bit in the beginning there of maybe it's a special customer that needs a unique color matching palette, or maybe it's a part that is, as Tim was saying before, it's what we would consider high volume, a few 100,000 units, but they all need to be exactly the same color. Really hard to do that when you're mixing chemicals on your own or making batches in small volumes that have really short shelf lives. So that's where the DM60 comes into play, and it, again, is a completely hands-free process. So the user is really just scanning a cartridge which is already identified as what color, what material, and what process it is that has seen prior to color. And that's really important, again, because that goes back to your design, to your build phase. All these things play a factor onto how we actually apply color in the best way possible. Through the DM60, we are essentially using a high pressurized water bath. But the process of adhering chemical is very different from a standard stain or paint. There is no geometric change to the part. It's actually going into the part. On general terms, it's around 200 to 250 microns of penetration depth. What that enables is we now have no worries of scratch resistance or that color coming off the part in normal environments. It also means that whether it's say it's a part that's being assembled to something else, now we don't have to consider as many worries of transfer, so dye transfer, standard testing in that regard. Another way to think about it is our applications that we'll talk about where maybe that part is in an external environment where it's seeing UV issues. standard dyes and standard paints will be affected really badly by different environmental aspects, whether it's temperature, humidity, or UV light. The dye that we do have, and a couple different options, we even have a UV stabilizer for one of the options, which allows you to actually enter into some of these markets at high volumes and still meet all the requirements that are setting forth. So, you learned a whole lot about who we are from company-wise and a lot of information about technologies. Now, why we're actually here is, what does that even mean? How do we apply this to real-world stuff? The next step of what this really looks like, I'm actually going to hand it back to Tim in a second here, but so you understand where everything lies as a picture, so you can kind of get that idea in your head again from the initial design phase to the print phase to the post-process phase. From the design and print phase, well, that's why Tim is here, right? That's why Stratasys is here. The relationships that they already have in place from the designing portion of this to the actual printer and the technology behind SAF. After that phase, it fits right into the normal work process flow that we already have implemented and proven throughout the industry for many years already. And that goes into play where it always starts from the cleaning side. Again, it has to be cleaned, right? It's the first step in all powder bed technologies. The next step is where we have to decide what that application is used for. What is that end requirement? Then we can decide what path it needs to go on. Top path is through just the coloring and surface finishing and mechanical method. So that's the really quick processing steps, and that's for the normal applications. The second and the bottom half of this is where it would lie into the more unique scenarios where it would need a totally sealed surface. What you see here is actually a totally different process step, right? Color is done before mechanical smoothing, but color is done after vapor smoothing. This is where it's really important to actually take these things into consideration, because maybe we need to actually consider how we implement this into a high volume application. The change in process steps will change the way you need to think about how we make that part in volume. So this is a really cool picture to see, and these are actually parts that we have up here. On the far left is actually something brand new. That's the PA11 material, brand new from behind the SAF technology. As Tim already explained a little bit about it, already comes with some really awesome properties right off the print side. The next step, and you see in the center, you can see some of that difference on the surface texture and the way it looks. That is just a straight path on the top half of what we just looked at. So that's the polyshot finish with the dye. Dye first, then surface finish after. Part all the way on the right-hand side is the bottom half of the path that we just talked about. So that's the vapor finish, and then dyed afterwards. So really cool to see those, and again, we have those parts right up here, so you can actually see firsthand what they look like, what they feel like, difference in weight, if at all, there's none, and then surface texture and look at the actual geometries, what may have changed, and how that process looks. The reason we have that picture up there is to get your brain flowing a little bit towards that end use, what those applications really are. So I'm going to pass it back over to Tim, and we'll talk a little bit more about the vision side of this.
So the why is Stratasys and Dimension doing this, right? Stratasys, we learned a long time ago, even when we weren't in the higher volumes, that people need more than just exactly what comes off any given product as a 3D printer, right? You have more requirements. What we recognize, I would say Scott Crump recognized it back probably almost 20 years ago, was that the layer thickness on an FDM was often not the desired surface finish. And so people were saying, hey, how can I get this kind of a look, right? So Scott started pushing internally on the development of vapor smoothing for FDM parts. So actually, when we talk here, even though I'm representing SAF, that doesn't mean it's the only application for a Dimension product. It could actually apply to different technologies within Stratasys' portfolio. But anyway, if we look back, Stratasys developed vapor smoothing, even got patents on it, and we had our own machine, for example. There we go again, okay. We had our own machine. Now, we don't sell that anymore, but we saw the opportunity here because we're getting into higher volumes. We need more automation, more opportunities for different surface finishes, whether it's colorants or whether it's smoothness or whatever, and we have to clean our parts. In SAF, you have to blast the powder off, right? So we needed some solutions like this, and we recognized the need to do things beyond the printer itself. It started way back then. And as part of this relationship this week, we're able to do a patent exchange where we can give use of our IP to DyeMansion, which is exciting because then we don't do that internally extremely well, right? So we can take our output and give it to another expert process to give the customer what they really need. thinking about that. Now yes, we make printers, right? We sell printers and all that stuff. But users want that solution, but what better way to test that solution than within our own house? So many of you are probably also aware, Stratasys doesn't only sell machines, we sell parts through something called Stratasys Direct. So Stratasys Direct is actually a very high volume parts producer and this is a trick actually. Anyway, we're a technology agnostic when it comes to additive. In fact, we have things which are not additive. So we manufacture in a lot of different ways at Stratasys Direct. So not only do we additive and other ways to manufacture things, but we have needs for that post-processing as well. So we test some of that stuff in there. We have different solutions. And one of the things that we're going to be doing very shortly is testing in bigger volumes the technologies that you see presented here today from DyeMansion. So we have an opportunity to test them before customers might wish to deploy them at their own sites.
That's exactly right. And the whole point behind that, as Tim said, is to test it, right? Field test it. It's kind of what we talked about in the beginning of having a couple different facilities with the technology there is to test them. The whole point is to actually prove it before we just throw it into the mix of hundreds and thousands of units. So where do we stand today? There's a couple main pillars in different verticals that we actually already have a ton of work in. And a lot of you, again, you're here because of that, right? So you already are aware of a lot of these different areas, and you're probably working in most of them, if not all of them. The industrial side is a great example of where 3D printing is really easy to implement. Replace spare parts, get rid of inventory. That's one of the big reasons additive came around, is getting rid of inventory. Space on shelves is really important. The right finish is also really important in those processes because chances are something that's in the industrial environment is beat up. Traditional printing methods, it might be easy to keep replacing that part, but over time that becomes pretty expensive. So having the right surface finish allows you to actually beat that part up and extend the life of that part as well. Then of course there's always the color side. Orange, of course, very industrial. That top left example is one of our biggest customers, Pro Glove. It is a fully printed component, which is an electrical item on the inside, and that's a handheld scanner. So that's eliminating one hand from needing to always be holding a scanner from the actual environment and inventory stage. So now that user is having two free hands, just having a scanner on top of their hand. We've seen plenty of their products go out, and we've seen them come back totally demolished. That's why we've run it through the different process to actually enable it to be beat up, run through all these different processes, and we do have a couple of different colors with them that mean and signify different things within their production floor. The automotive sector and the medical sector are really key ones to show off certifications. Now again, of course, medical makes sense, right? Medical has all the different certifications around biocompatibility and everything that's encompassed within that, which is very difficult to understand sometimes. The automotive sector, also very difficult to understand. Automotive sector has your basic ISOs, but then guess what? Each one of the main OEMs has their own one that's a spin-off of what that ISO is. Standard ISO certifications for light and heat resistance. GM has their own, Toyota has their own, Ford has their own. They're all spin-offs that maybe it's only a little bit of a variance, but it's a really important factor to understand when you're making that part, how do you actually meet those certifications? So we already live in that bucket as well, as we explained through some of the different processes. And the last one, which is pretty personal on my end, the consumer side. I actually came from a consumer good products with printing. There's a lot of really tricky things about this because you're not just dealing with products that are always in use, you're dealing with opinionated customers too. People that have what we generally call in the consumer world the 3-foot rule. If it looks good from 3 feet, which is an arm's length when it's on a shelf, then it meets most of your standards. But that's also something that's put to the test because that person might be someone buying a product in Texas or someone in northern Maine. Two totally different environments, two totally different temperature ranges, and two totally different ways that they're probably living and beating up on that product. So it still needs to be able to perform to actually be applicable in real world situations. So that's kind of where we live so far. And that's strictly on the power shot side. So again, that's just the mechanical surfacing finish. So it's the easiest step into the market, but it kind of shows where we already lie just on those simple verticals with a really simple process. Taking it into the newest technology that we have, the vapor fuse technology, where do we currently lie with that? Similar sectors, of course, just different standards, different certifications that are needed. So again, in that industrial environment, now we can deal with things like ventilation tubes, venturi channels, anything that needs to process and flow air or liquid or anything like that. Now these can all be printed components that needed traditionally to be a totally smooth inner channel to actually process or work the right way. Standard porous materials off the print will not perform that way. Smoothing that part can actually enable that. The automotive sector is a really interesting topic here because not only can it be end-use parts, but it can also be parts for prototyping. A really cool example of this is standard prototyping engine blocks or manifolds, things that are actually put to test. Porosity kills that test. A part coming off the printer generally goes through several other processes just to be tested. Whether it's sanded, then epoxy dipped, sanded, and epoxy dipped again is usually a standard process there. Vapor smoothing that part eliminates all that testing, all that extra work and handwork, and now it can go right into a testing phase. So it doesn't have to be an end-use part all the time. And this is where that, keep in mind of what is that application, how is it actually being used, then think about the process that you apply to it. Consumer sector, again, this is a little bit tricky because usually it's about a visual aesthetic at this point. Consumers are very opinionated on this, but it also has to meet certain standards. We have to be able to beat up on that product again, but still remain visually appealing. Food and beverage is very similar to the industrial side, where it cannot, or it doesn't always have to be on the end side. Of course, it's not going to be a food product, right? You're not drinking it, you're not eating it, but maybe it's used to hold that product, or maybe it's a plate that needs to be washed, or maybe it's an actual gripper that moves parts, a pick and place type product. We have a lot of applications that are already using that kind of technology, and the reason they're using a vapor fused part is because now it's a smooth surface. When it's a gripper that moves back and forth, particulates don't stick to that. Where if it's a porous part, particulates now stick to that. Now they have to interchange that part or stop production to clean that part. Smoothing that part enables them to continue production lines without stopping. It's a really cool thing to think about, and a really simple process. So those are some of the areas that we currently live with the two main different types of surface technologies, all of which have their different requirements for color, of course, and everything always starts with cleaning. So the two main areas that change are the two surfacing technologies. As we talked about a little bit of why smoothing an object might be really beneficial to you, one thing to think about is our inner channels. Why does it work in an industrial environment? Smoothing a product totally smooth on the inside of a standard tube allows for the increase of airflow, increase of water flow to actually meet what you're actually designed. That napkin sketch that you designed, when you print it, you want it to meet what you actually wanted to do, right? So smoothing it through our technology, we can actually reduce the surface roughness by over 80%, which is huge. It's not perfect, obviously, but it's really, really close to getting there. And what that enables, as I said before, it actually means that your part can now do what you want it and intended it to do. The other side of that is now it's watertight, now it's airtight. And we've actually been able to prove and test this, and we have a lot of these videos online so you can actually see how we did it. These are not ISO standard tests, right? These are putting the test to an actual, or putting a part to a test that we've created to actually see what it looks like, to actually try to make it fail, really. So we've actually seen that we can totally seal a part underwater, and we've actually used, I believe this was 4 bar, as a wall thickness of down to 0.45 millimeters. Now, what does that mean? Think of it from the cost side of things. Now we don't need as much material to create a solid wall that needs to be used in an airtight environment. We can use less material on the design side, save money over time. All we're doing is changing the finish. Not only do we have to think about, maybe we're using less material, but now we can use a different design. Maybe we can actually, this wasn't an area that we could do before with 3D printing. Now we can actually 3D print something, get rid of a traditional manufacturing environment, have a sealed surface, and now enable a product to be used in an airtight environment. The last one is also very important for industrial environments or medical environments. A surface that now can be used, cleaned, and beat up with harsh chemicals. So what we've seen through different testing and industries that we're already in and products that are in the market currently is that a part that's now been smooth can be used in areas with harsh chemicals like oils. And now even crazier than that, the oil removers. So chemicals that are meant to demolish the way particulates stick to another and then remove them. What we've seen is that sealed surface actually stands up against that. So now that printed component doesn't have to be scrapped once we use it in an oil environment, like a filter, for example. We don't have to toss that part and reprint a new one. We can actually just seal it and enable that part to have a repeatable life cycle. So really cool to see where we were, and now I'm going to hand it back over to Tim to see what is the future of that.
All right. So I mentioned earlier a few of the features that we have in SAF or in our H350 technology. That's a picture of the machine if you haven't seen it yet. But our three cornerstones are about the consistency of the part, controlling your cost, and controlling your process, and make it your own, certify what you need, use the data you need to certify what you have. We're serving, of course, those same industries that Mike was talking about. But let's look at some of the parts. Now, we have some parts up here, and we don't have a plethora of them out there for you to look at yet today, right? But one of the things that we see, along with the consistency of just mechanicals and accuracy and stuff like that, are surface consistency, right? So what do we do really well? Well, we do some fine detail really well. I have this part up here as well. We do bulky parts very well, which is maybe a strength for this powder bed fusion compared to some others. You know, I'm not an expert in all of them again, right? But it is nice that we can do bulky parts without a lot of challenge. We have good surface consistency. We could imagine one day, maybe we will have an end-use part. It'll be this part in somebody's hand. Maybe it'll be vapor smooth. Maybe it's smooth enough to be a consumer part. That leads to my closing comment. All right, you look at this. It looks really great. We talk about end-use parts, right? Okay, we're going to take a part like this. Is that end-use? I don't know. Tim's not going to get on and buy it for $5 at Walmart. So I don't know. Is it end-use, or is this a component that's going to be in an end-use part? This is probably going to be in an end-use part. What's the end-use product? It's a car, right? So now you start thinking, you go, well, what's the real thing here? The real thing is, we've always talked about in additive manufacturing, how could we disrupt supply chains? How can we affect inventory? How can we get to an end-use part? How can we get volumes of parts? How can we maybe compete against injection molding tools? Because we don't replace them, we all know that. But if you find new ways to bring in ROI and new ways to introduce applications to additive manufacturing, which will eventually become an end-use product, maybe we will affect that supply chain in different ways than we ever did before. But to do that, we have to consider that 3D printing is just a piece of that supply chain. And even if it sits in this room and I have an H350, well, I have front-end stuff to manage. I have to manage the design. I have to manage the data. I have to track that data and trace it through with the part. Then I have to get to the other end of the machine. Now I have to clean the part. Now what? Well, I need a smooth part. I need a colored part or whatever. That's where maybe dimension is. Then you go, well, what if that connector needs to go into something else? Let's not say a car. Let's say something smaller. So, well, maybe we need automation. Maybe we have to have an automated way to get the parts out of the machine and then do something with them. Maybe do a machining operation, right? You could machine an additive part, and then maybe it moves to another work cell and gets added to something to create a bigger assembly, which becomes an end-use part. If we're really going to do supply chain, it's not just 3D printing. It's more than that. So from my perspective, and this is Tim's perspective, we have to create an ecosystem of more things to complement additive and let additive make a great core, but then let's add things to create the real supply chain disruption. We found out last year how supply chain can be disrupted in the wrong direction. Let's help disrupt it in the right direction, right? That's where we want to go.
Yeah, and Tim's exactly right. The idea is it's the vision moving forward. We talk about all the applications and places that we're already at. But we have to understand that there's still a lot of work to do to get to that next step. And the whole idea behind this is to help create that vision, enable you, right? But to just really get the brain flowing. How do we all work together? And one of the ways is what we're doing right now is creating an alliance with using the strength and the knowledge between two different companies, applying it together to create a totally full solution from the design side all the way to that final part. There's still missing pieces, of course, there always are. But the idea is to help fill in the gaps and create that future vision as we can move forward. So I apologize. I know we ran a little bit long. We also started late. Floor is totally open for questions. The next slide is just the Q&A, so might as well leave it up here, some contacts. You can take some pictures. But if anyone's got any questions, feel free, please.